Mr. Chairman, I'm very happy to announce this is the last session in our beautiful workshop. So, also good news, we only have 3 lectures left. And so the first lecturer, Professor Lee from Imperial College. And so please, yeah, you can start. Coarse Curvature.
Thank you very much. Since in the last session, I try not to be heavy on this. The name is Coarse Curvature, but the reason I chose to talk to this, I think I had a conversation with Tassi, and she thinks this more applied to people. Maybe it's more interesting to everybody. But I would just have the first slides to keep in touch with everybody else here. I'm looking for input to doing theoretical stochastic analysis. So I'm like to know, I'm looking for input. This is the topic I will be talking about today, the coarse extrinsic curvature. It's the beginning of a project. It's a project somewhat not related to my recent work, other recent work, and not too much related to my past work either. Maybe it's going to be future work. So we hope going to be related to manifold learning from a noisy data cloud. We hope also to develop it for graphosymmetric spaces. So just let me know if you have some ideas. The other ones, I'm looking for some input with some stochastic model I have been working on. So mainly I work on multi-scale. One of the topic is there's a 2-scale system, say 2 families of random variables evolving, interacting with respect to each other. The object of interest would be set on its own scale. So it be take time t to say 0, 1. And the yt epsilon is typically fast and ergodic. And so this one we are most interested in was 2 things. So one is set it on manifold. The second one is long range, say, autocorrelated noise. So for Markov process, for random dynamic system has been existed for a long time. You take a Hamiltonian system with conservation law, then you expand in epsilon, the first order is average and second order is something. And so for Brownian motion is also quite well known. One is called stochastic averaging. The other one's called time homogenization. And there hasn't been much of progress in the non-Markovan front. So here we developed a lot for fractional Brownian motion here. So fractional Brownian motion for h bigger than 1/2 is slow diffusion, is sort of smooth. For h smaller than 1/2, it's much more non-smooth compared to Brownian motion. It has all this dependence. It doesn't matter how far you take the time scale, is correlated and decays polynomially. So, but it decays not very fast for h bigger than 1/2. So this we develop it, and I'm also interested to see models which be relevant from application. So let me know if you know some or you want to discuss it. The other ones we are looking at SPDEs, because one of my main endeavor recently is a long-range correlation. So for SPDE, we talk about the spatial correlation, which is long-range. White noise convolved with a function smooth, but not compactly supported. And then you want to know, so all the physics probably knows, if you have compact support of fast speed as our first talk, if fast decay, and the correlation always decay, sort of vanishes after evolve with the system for a bit. And this we are pursuing persistence in correlation on fluctuation theory. Now I come down to what I want to do. This is kind of a new thing. My PhD student, Ben Pettico, he came to me, he had lots of application in mind. He wanted to look at data, and I know nothing about data. I said, look, I'm a classical stochastic analyst, very theoretical. So what you want to do? We checked a few things, didn't really work out. So then he come up with this paper. How about the Oliver's coarse curvature? I look at it and said, okay, let's look at it. So what does it do is, oh, interesting. I did something stupid. What did I do? Okay, so if you take two measures and you wanted to know the transport cost from one location to another location, or rather, there's two measures you want to transport it. You want to look at the transportation distance. It's most commonly used for L2. So L2 is very easy to do analysis. It's standard in the literature. Well, L1 is also a beautiful advantage. We're going to see it. So we take a Watson distance between two measures, which means integrate with respect to a measure on the product with marginals to be two of the measures you started with. And integrate over and take a minimum over all such couplings. And that's the Watson distance. And sometimes it's given by optimal transport. In that case, the measure would be focused on the transport graph. So that's a transport map. How does it relate to curvature? Suppose you are on a sphere and you want, or even a ball, and want to know what's the curvature. So the idea is the curvature, especially rigid curvature, actually controls the volume of a geodesic ball, certain radius. You look at the volume of geodesic ball and a certain radius, it's typically comparing it to a model space of constant section curvature where you can compute. So if it's rigid curvature bounded from below by the dimension minus 5 multiplied k, then you look at the model space with the curvature k, then the volume will be controlled by the volume on the model space. So somehow you see the rigid curvature, the lower bound of rigid curvature. Now, idea came with Olivier is that suppose you take a family of probability measures. So you have your space. At every point, you give it a measure. So typically thinking about the uniform measure, the volume measure or the Lebesgue measure, you restrict it to a little ball of that specific point and take the balls sufficiently small, say size epsilon. And then you take 2 points delta distance from each other, and you look at what's the distance of the two volume measures. Okay. Well, that's related to transportation. So what you do, you take one measure, transport to the other one, then you look at the distance between the transported one and the original one. So that one differs by a certain order of correction term, it's a good order. Then you just look at the image measure, and then and the one already there, you look at what's the distance. And of course, it should depend on the rigid curvature because curvature is like a gravity. It's it's like if you think it's positive curvature, it's like going up a hill, right? So you should feel the curvature. And so it turns out if you take the normalized Lebesgue measure on a certain radius epsilon with certain distance, you're going to see the rigid curvature. And so from people working with probability, this family of measures you can take it to be, say, hit kernel measure, sitting upon the transition probabilities. So you have a family of probability measures. You want to know whether it fills the curvature. Now, here's the definition. So this is the green one's volume, the geodesic balls of size epsilon sitting at point X. And we restrict it to this ball, and this is the volume measure, and here's the renormalization constant. So this is the family of measures one considers. And you take 2 points, distance delta apart, like these 2 points. And but thinking why, well, they're small enough for these 2 points will be on the geodesics. So take V to be the direction, normal 1. Delta will be the distance. And what he defines is he take the less than 1 distance of the 2 measures, this between the 2 measures, divided by the distance, and subtract from 1, and that's the negative of rigid curvature. That's what he claims at point x0 at scale epsilon. So this is justified by a computation on Riemannian manifold. So if you take the less than distance expanded in epsilon and in delta, so this quantity is 1. So first order, this is just 1. The correction term is rigid curvature. In the order epsilon square, there's no first order term because some averaging effects. So it's a second order correction with dimension appearing here, otherwise you see clearly a rigid curvature. And then the next order is order 3. So there's clearly object. If we move everything to the other side, throw away this order, that should be the curvature. So that's his idea. He defined it to be coarse rigid curvature. Now, why is it useful? If you have a manifold which maybe Lipschitz manifold, you have a folds, or you have a graph, there's no differential structure. And this is a potential candidate for a curvature to play the role, whatever you get from rigid curvature in the smooth manifold. Right, so just briefly explain what the curvatures are. These are the 3 spatial forms. Positive constant curvature, negative constant curvature. This is the hyperbola sort of sphere, and that's a flat one. So that's 3 spatial forms, which we used as a benchmark for our computations estimates. Now, the Riemann curvature operator R, it a vector. So here I take a vector field, but it 2 tangent vectors, and that's a 3rd tangent vector. So what it is, it tells how far the differentiation of Z in 2 different directions, y first x, then first x, then y, how far they are from failing to commute. That's the curvature. And the important thing come out of curvature is a sectional curvature. You take 2 directions, u and v, And then this RUV, so if they are orthogonal, that's RUV is a sectional curvature. So you sort of, you have a plane, you want to know how the plane is bending, which direction is bending. And the rigid curvature is a sum. You take an orthonormal basis of a tangent space, a sum of all sectional curvatures. So, trace. Okay, so that's a rigid curvature. Now, how does it comes in compared to the definition, the Western one distance? Here's one thing. If you have a geodesics, say I set it on this perfect sphere, you have one vector here at the tangent space at one point, and you have a vector field along the curve. You want to differentiate. But what does it mean by differentiation? They are at different spaces. So you can't different things at two different spaces. What one does is try to translate all the objects into one space, and that's called a parallel translation. You do it in a way conform with Riemann metric, so orthonormal objects remain orthonormal, so that's the parallel translation. So this is use a double sign, so the parallel translation along a curve. So once you can do that, then one can define the concept of differentiating a vector field. A vector field at each axis belong to one vector space, so you move them back, you differentiate. So that's a covariant derivative. The other thing you're thinking about is if you have embedded manifold in Rm, you differentiate a vector field as if we're in Rn in certain direction. But then you have to project back to the tangent space. So that projection defines Levi-Civita connection. So that's a curvature. Here's my collaborators. Ben Petticoat, and he's the one who reviewing about doing a bit of geometry with me. He came to me, well, no, I was going to do stochastic, but I heard you were expert in geometry. Can't we do some geometry? And so Mark Anodon, we collaborated about this work. So the first piece of work is coarse rigid curvature is actually generalized rigid curvature. In probability community, it's called Bakri-Emery. And so it's a coarse rigid curvature. And this one, we send, so what's the story? The story is we look at Oliver's proof. I had a problem to understand it. And so we said, the best way to do it, let's just go through the proof. And we fill in the gap or correct some wrong concepts to make sure everything works with all the correct geometric estimates. Because he was interested in going to graph. He's justifying his definition, and he has this proposal for proof. Is essentially all good ideas, is based on the following concept. Everything small is essentially Euclidean, but it's not essentially Euclidean, sometimes it doesn't work. And the computation for errors, it's not a Euclidean computation. So we did this at some stage, and that helped us to understand it. Well, being me, I would never read a paper without do something. I said, look, there's one thing interesting. There's several things interesting. One of them, we tried for a long time with some geometers. It's being pushed back. But one of them is the easiest trick is we take a measure, but if you're doing diffusions, you have your Laplacian, you have some gradient, some potential, gradient of potential, the drift. And together, not separately, they play a good role. That's a sort of rigid curvature, sort of generalized rigid curvature. Said, can we do that? So the natural thing to do is now you found your measure, which now I call the test measures. You take a family of measures, you choose them to be sort of again uniform, restricted measure from the weighted measure, right? So thinking about we are having a Laplacian plus gradient of potential. So the function we are interested in is minus v to the dx. So we take that measure. And indeed, that actually worked. Then we realized that somebody actually did some work on Poisson-Pont clause. And I'll come back to that. We did this. And then we got, actually we sent to the AMS. We thought we can get a more general audience for a general journal like this. I had 3 reviews, it's all very positive. So we're a bit encouraged of that. And then we start to do the second one. Then we started really thinking about the application. How do we do it? Do we do a simulation? Do we go to graph? And do we really get some data? But when doing this, I start to think, how do we get the data? Typically, you send your beam into a surface, you get a reflection. You collect this data. And the data tell you something about the surface you're interested in. What do I know about the curvature? The curvature is a strange thing, right? It's non-commuting. If you take a one-dimensional thing, a circle, there's no curvature. There's no commuting between 2 directions. It's flat. But if you want to look at this from the point of view of, or you can take a donut, and you want to see the shape of donuts, it's flat, but it has a shape. We just realize rigid curvature probably is not the right thing to do. And we want to see the curvature as you would see it in ambient space. In other words, asymmetrically embedded submanifold for Rn. So that's where we start to do the second one. And that we had a lot of difficulty because you see the rigid curvature is actually makes some sense because there is a theorem if you do a damped parallel translation and then this is an object you see very often in stochastic analysis. You have rigid curvature, you look up, you parallel translate your object, you see rigid curvature. Somehow you understand that there is rigid curvature there. For us, we didn't understand what's going on at all. Okay, so now this comes down to important objects. What's the test measure we need? As I explained, if we want to take a Laplacian plus gradient way, we will take this weighted measure. And lo and behold, we did have the result we want, which is exactly the rigid plus twice of Hessian comes in together in the right order. So I give you a quick proof of this object first. So what happened is we have a measure here. We want to look at the transport distance in L1. And it's very difficult to work on the manifold, but this diffeomorphism, local diffeomorphism between this one and the geodesic pole on the tangent space. And so this passes this measure to another measure. So there are two measures here, there's two measures here. And there's also the measure we could transport it to here if we choose a good enough transport here. And this map and that map has very small, they are very close. Well, no, this one is too very close. The density is very close with certain error. Then your Watson distance also close. That's easy to check. So that means that somehow after you compute this is more or less causing no trouble. So we could work on the tangent space after all the corrections and done. And difficulty is we have to propose some approximate transport map, optimal transport map for that. So this is just explaining once we are here, we could try to transport one to here, from one to the other one by some kind of parallel translation, but take into account of a gradient function here. Okay, so the other thing which is getting closer to the application we have in mind, again on the rigid curvature front, is the following. Suppose we take some Poisson point process, sample it with a certain intensity, so the volume measure, but with proportional to the potential. For x0 is fixed because we are interested in the rigid curvature at x0. And so for each n, we do it proportional to this guy, but increasing the intensity as n goes up. So we have a sequence of Poisson point process. And then we take samples on the manifold. For each n, we got some Poisson random pulse. Now we take a sequence of delta n called a sequence of epsilon n. Epsilon n is a connectivity radius. Means look at all the Poisson point process. If their distance is smaller than epsilon n, we connect them. So we get a graph. We get a graph. Then you have the edge. The distance on the edge, we use the Riemannian distance. So this one defines a graph distance. When you have a graph distance, we could talk about geodesic balls on the graph. So this geodesic, once we've done this, we're going to take some uniform measure on the ball at each point of a radius delta n. So this is a test measure we have. So for each n, we have basically a graph distance. We have test measures, and that allow us to define this curvature for each n. And the theorem is as n goes to infinity, if you take your epsilon n and delta n to a certain order of n, and you recover the curvature of the manifold, because you have more and more points. Now this work for v equal to 0 in the uniform measure, uniform speed case was done by this Vanderholm, Kunihan, Lipner, Trugenberg, and Kryukov. We borrowed some results. They obtained the differences. We have to propose a different transport map. Consider V, and we have certain non-uniformity here. And so the theorem is saying is that, yeah, your connectivity radius obviously needs to be less equal to the test measure radius. And they don't have to be the same, but they can be the same to be both to be the order n to the minus alpha. And then alpha is a certain order here. Then there exists some constant go down to 0, such that the Western distance of this uniform test measures at level n with radius delta n from each other. This is sitting at yn. Yn would be distance delta n from x0. And look at this graph distance in the graph Gn. And then we look at the Western distance of the measure on the manifold. And they are very close to each other, again to the order 3. So as a consequence, that means if we take the random geometric graph, and then we compute the curvature, and n should be dimension. And then the capital N is the dimension. And so this object, again, gives the radial curvature plus Hessian V. So this is where we hope to inspire us to do a bit more on graphs in this theory. Am I over? How much time do I have? 2 minutes.
12, you can see.
Oh, 12. Oh, yeah, okay. I didn't know when I'm supposed to stop. Without a target, it's difficult. Okay. Okay, so that's now come back. We said we are interested in extrinsic curvature. Well, I'm in Lausanne. Every children learns from the books. I spy with my eyes. I see a cow. So now I'm spying with noise data. I see curvature. I see shape. So radial curvature, when I was working on geometric analysis, stochastic geometric analysis, trying to apply myself being real geometer, I would avoid at any cost of embedding. Any concept comes from embedding. And so you want radial curvature, geometers use sectional curvature, and the probabilities are proud they use radial curvature, it's summed up. And but nobody wants a second fundamental form or mean curvature because it's not intrinsic enough unless you're moving the object around, you do. But now we decided we're interested in the second fundamental form, which is also called the shape operator. So what is it? You take a vector field, W, at the point x is a small w. So the second fundamental form is the following. We differentiate W, and in the ambient space, it could be Rn, could be manifold. And we also differentiate on the manifold. Of course, the difference is the projection. It's asymmetrically embedded. If we project this down, it should be this. So there's a difference. That is a shape operator, which tells you how much everything bends. So second fundamental form tells us how flat something is, or how much it curves. And so the second fundamental form is less popular or less well-known. And so I would put the one which is the mean curvature here. The mean curvature is the one we take a normal basis. We take the second fundamental form in each of the directions and sum it up. It's average, the summed up stuff again. And you're going to see when we get a result, it's this would be easier, well, have this result, but it would be some kind of more directional, and this one would be not directional. Okay, so now come down to the question, what type of test measure will allow us to see the second fundamental form? If I'm looking at sort of a surface, like that, if I'm just choosing a piece of, as before, a piece of volume here, I won't be seeing much of the ambient space. I could compute using the Rn data, but if I'm good at it, I would eventually come back to the manifold with nothing else comes in. So that means the sort of test measure we have must come from ambient space, which is fair. If you shoot your laser beam to the manifold, you don't know the boundary of your manifold, you will shoot a bit randomly into a little neighborhood of it. So the measure we choose would be a piece of in the tubular neighborhood of your manifold. So in the case, draw a picture, if it is a curve, the sort of test measure would be a piece of interval of this, and it goes up like a square. So that's what a test measure would be. It's a boundary measure. And so in this case, one can compute what goes on if you have a curve. And the most interesting thing is you look at the oscular circle, which at this point would agree with the tangent plane. They have the same tangent line. And this guy, that's a radius. And that should be the curvature along the curve. 1 over r should be the radius, should be the curvature. So one look at this guy. So let me just say we define the measure, and then we kind of use a local computation, use an osculating circle along the curve at each point to compute it. So in that case, I just gave you the circle. So I'm taking x0 and y. We take a piece of measure here and then put it into a piece of measure here. We compute the Watson distance. So there's more parameter now, distance between x0 and y, this manifold direction, the radius, and also vertical direction, sigma. Now we compute, this Watson distance can be computed because if you take a perfect circle, you can propose a precise transport map and compute that, we get this mass. And especially we didn't quite like this sign. This is fine because epsilon go to 0, they are essentially this r. This one we didn't like much. But then it turns out, of course, if you write it down in the Euclidean distance, then this one disappears, you have a very nice expression. And that would be the second mean curvature. I think at this stage, I'm mainly happy. So let me give you the references. I have the rest of them will be detailed if you want to ask. But so I'm finishing my talk with the references. I went to Seville to give a talk on stochastic sewing lamp. I have nothing to do with this. At the airport, I was going with a colleague. He met 2 other colleagues in Norway. And My colleague sort of went ahead. He had flight quickly. I have mine in 2 hours, the other two have in 4 hours. And they start to ask me what I'm doing. And I start to tell them about raw pass, slow fast stochastic, maybe slow fast or manifold. And they're getting more and more interested in manifold. Oh, yeah. So then I went a bit more and more, they steered me to here. So by the time I told me this story, and we had a gap, they told me they put my paper out, and they are very, actually wonderful them, because the other one who turned out we met when I gave a talk on fraction Brownian motion. So this guy, let me see, what's his name? Lassas. And he said, look, it's very interesting to me because I'm working on it. I realized that now I saw his paper, I realized he's not bluffing. So there's 3 papers by a few authors, including, so Feifman, Ivanov, Lassas, Lu, Mariana, and Kirillov. They were reconstruction and interpolating data, noise data, and construct a metric. Use noise distance to construct a matrix. The fitting manifold of large range. So then I realized there's a community here, and then I dig a bit more, and then I saw lots of people are working out. To start with, there was, of course, this the community in metric space work on rigid curvature bounded from below, but that's a slightly different story because it's a very big industry. And then you get the people who are doing numerics. You see, this is geometers, quite a lot of geometers are working on Yo, and there's some stochastic people, and a few geometric analysts. Yeah, and even Yost also working on it. So yeah, so I was thinking, yeah, so I got a bit more interested in that. So that's my story. So I'm looking to get ideas for progressing. If you have ideas, let me know. I appreciate actually, I didn't know what to talk about, so I thought that this might be more applied than what I normally do. What I normally do is very much stochastic analysis.
Right, thank you very much. It's around 2 minutes left, and we have time for a couple of questions. Right. Oh, yes, please.
So, I mean, at the moment you are observing, you're thinking of data on this manifold, noisy data on here, which is the positions, right?
Yeah.
So, if instead of positions, say, I mean, I imagine a hill, and then instead of measuring where the points of the hill are, you measure the trajectory of something rolling down the hill. Can you then try to sort of indirect, this sort of indirect?
Well, if you have a data, so I'm thinking about you're in an ambient space. You actually don't know where the hill is. If you took a path which happened to pass a hill, you can probably compare to the distance to the ambient space, since you would tunnel if you're ambient space. If you're on the hill, it's lots of effort. The distance, right, to go up. You suppose you don't know where it is. You want to tell it's from you're on the hill or you are, and.
But the velocity, shouldn't that tell you something?
If you want velocity, you have to make the intrinsic, because you cannot use gasoline to speed up, right? Or even an electric car doesn't quite work. So if you want the velocity, I would have to work with some Hamiltonian functions, my energies. functions. If you want to tell anything from the velocity of certain things. Otherwise, it has to be intrinsic sometimes. So GD6 are intrinsic. Energy minimizers are intrinsic. But you could, I haven't, could be interesting.
Okay, so any further questions? Okay, thank you again.